Let's look at an expected value example involving a dice game. In a particular dice game at a state fair carnival, the player wins $10 if a 6 is rolled, the player wins $2 if a 2 or a 4 is rolled, and the player wins nothing if they roll an odd number. Let's assume this is a standard 6-sided die. To organize ourselves before we find the expected value, let's create a probability distribution for the amount won by a player in a single roll of that 6-sided die. Now, there's really three things happening here. We've got the first situation where a player wins, which is they win $10 if a 6 is rolled. The other scenario is that if a 2 or a 4 is rolled, they win $2. And then if an odd number is rolled, they win nothing, $0. What we also need, in addition to kind of recognizing the three things that could happen, is we need to know their probabilities. Well, in a fair 6-sided die, to roll a 6, there's 1 6 out of 6 options. So that's a probability of 1/6. If we want to roll a 2 or a 4, that's 2 of the options that are on the die faces out of 6 total. So that would be 2/6. And then to roll something odd, there's a 1, a 3, and a 5. There's 3 odd numbers on the 6-sided die. That's 3 out of 6 options. So my probabilities are 1/6, 2/6, and 3/6. To double check that I've done this correctly, that I have a probability distribution, remember this should add up to 100% if I add the probabilities. 1/6 plus 2/6 plus 3/6. That would be 1 plus 2 plus 3 is 6. 6 over 6 is 1, or remember 1 is the same thing as 100%. So we do have all of the options taken care of in this table. Now to find the expected value, I'm going to take the value of the event and multiply it by its corresponding probability for each event that could happen. Then I'm going to add them up. So I'm going to add them up. So because you've organized this into a table, it makes it a little bit easier to see what you're calculating with. I'm going to take $10 times 1/6 plus $2 times 2/6 plus $0 times 3/6. If you want to do this piecemeal, do the multiplication first, then add up your values. But if you have a scientific calculator, you can enter the whole thing in at once. And that's what I'm going to do. 10 times 1 divided by 6 plus 2 times 2 divided by 6 plus 0 times 3 divided by 6. Hit enter, and what you should get is 2.33333 going across the screen. Because this is an amount of money, we're going to round at the nearest cent, so $2.33. Now let's interpret this in terms of the situation and the meaning of expected value. What we are looking at when we calculate expected value is the average value of the game, in this case, or the event, the experiment, if you play the game many times. So in the long run. And what we were looking at here was how much the player would win. So in the long run, over the course of many games, after many plays, the player will have won on average, and it's very important to say on average because this is an average amount, $2.33 per game. All right, so this is an average. They will never have won in a single game $2.33. Remember, in a single game, they're either going to win $10, $0, or $2 or $0. They can't win $2.33 on a single game. So this is an average amount. $2.33 is the average amount they would win per game if they played many times. Okay? Now, where this is useful to the casino is they can calculate this average winning for the player and they can decide how much to charge a person to win the game to make sure they make a profit. If they were to charge $2.33 to play the game, the casino would break even, or the carnival would break even. In other words, they would give out as much money as they're bringing in. But that's not what they want to do. They want to make a profit. To make a profit, they need to charge more. So they might charge, if they only want to make 1 cent in profit per game, they could charge $2.34. But generally, they're going to want to charge a lot more, maybe $3, $4, $5. So to make a profit, they want to do something definitely more than $2.33. Here we'll look at the expected value of a game played at a charity event. A door game at this charity event involves drawing a marble from a black bag with 20 marbles in it. 12 of the marbles are black, 1 is yellow, 6 are orange, and 1 is red. Depending on the color of the marble, the player either wins some money or donates some money to the charity. If they draw out a black marble, they're going to win $1. If they draw out the yellow marble, they win $100. If they draw out the orange marble, they donate $10. And if they draw out the red marble, they donate $75. So let's look at organizing this information and all possible things that could happen into a probability distribution. And I've put the table above here. You'll notice in this table, I have things organized slightly differently. I've got the values of the events in columns and the probabilities in the next column over, instead of horizontally in rows. Probability distributions can be done either way. The main thing is to label them. So you can always have them horizontally or vertically, just depends on what kind of fits on the page is kind of how most people choose. So if we think about all the things that could happen here, we've got a black bag with 20 marbles, and there's only 4 colors of marbles. So they could, you could end up drawing a black marble, a yellow marble, an orange marble, or a red marble. The value of the event, well, for a black marble, you win $1. For a yellow marble, you win $100. For an orange marble, you donate 10. Now, how that would be said mathematically is you'd say a minus 10 for donating, negative, and then red marble donates $75. So negative 75. Now let's think about the probability of each of those things happening. For the probabilities, we need to think about the total number of marbles, which is 20, and how many options there are for choosing a particular color. Well, there's 12 black marbles, so I could, the chance of getting a black marble is 12 over 20. There's 1 yellow marble, so the chance of getting a yellow marble is 1 out of 20. There are 6 orange marbles, so the chance of getting an orange marble is 6 out of 20. And 1 red marble, and the chance of getting a red marble, therefore, is 1 out of 20. So we have our information organized here in the table. If we next want to find an expected value for this scenario, we want to think about looking at the value of each event and their corresponding probability. This time, they're right next to each other in each row. And we're going to multiply each value, including using negatives when I need to, and their corresponding probabilities. Then we'll add them all up. So that it's nice that the information is organized in that table to help you out. But let's write it down. $1 times 12 over 20 plus $100 times 1 over 20 plus, well, negative $10. And there are 2 ways you can do this. You could use plus and then show the negative 10, or you could do minus 10 times 6/20, and then plus a negative 75 times 1/20. And I forgot my dollar sign there. I'll sneak that in. So calculating this, again, I'm just going to use my scientific calculator where I can enter in everything as it is. So instead of doing it piecemeal. So I'm going to say 1 times 12 over 20 plus 100 times 1 over 20. So remember, 1 over 20 is 1 divided by 20. Plus a negative 10 times 6 over 20. Plus negative 75 times 1 divided by 20. So again, every fraction can be entered in as 1 divided by. If I then hit equals after putting that whole thing in, I will get negative $1.15. Now again, let's think about what this means. Negative $1.15. Remember, this is an average amount that, and we're looking at this from a player perspective, an average amount that the player is going to, negative means donate, if they were to play this game many, 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 many times. So from on average, a draw from the bag will result in the player donating $1.15. All right, what does this mean for the charity? Well, the charity is going to get money on average if this game is played enough. So if this game, if enough people play, if enough people come to go to the charity event and enough people play, this charity is going to make money because the player is donating on average. And so the charity is getting that money they've donated. So in the long run, if many people play, this charity wins money. So it's a good thing for the charity.